Hi everybody, and happy summer 2026. Just a few weeks ago, I was up in Alaska filming a series of geology videos with 4 geologists from Purdue University. There's a number of these videos that will be coming on this YouTube channel. I hope you enjoy each of these. First up, Wrangell Volcanoes.
So this is one of the neatest places in Alaska because you're driving along. We've been driving it through the Copper River Basin towards Glen Allen, and then all of a sudden you see these big mountains here and they're isolated by themselves, but they go all the way to the Yukon Territory, and there's a line of them.
Let me zoom in on this one right here. What's the name of this guy?
This is Mount Drum here.
Mount
And
Drum.
these are active volcanoes. And so the question has always been, why are they here? Why are they in this odd area? And we've never been able to answer that very well.
Okay.
But what's always been intriguing about the tectonics of Alaska is that you have the Aleutian Arc that comes up to Anchorage, and then there's an area through here that we call the non-magmatic gap. So here's Anchorage. These are the Aleutian volcanoes.
Good.
There's this big area that's almost like a plateau called the Talkeetna Mountains. And then we're over in this area in eastern Alaska. And you can see all these active volcanoes, and they go all the way down along the Denali Fault. So the tectonics of Alaska used to be, when this whole idea of terrain accretion became important, was that during the Cretaceous, terrains were colliding, transported to the north, and you had this shortening when they hit this big bend in Alaska.
Mm-hmm.
But now we know that much of the tectonics of what we see in Alaska is driven by what we call flat slab subduction. And this has just been recognized the last 20 years by a wide group of geophysicists, thermochronologists, sedimentary geologists. And what they were able to determine first with offshore geophysics is that there's a thick piece of continental crust out here that's labeled the Yakutak microplate.
Sounds familiar.
It's very familiar because down in Washington, you guys have a very similar related oceanic plateau. So this is greater than 30 kilometers thick offshore. But with geophysics, we've been able to show that it extends all the way. So here's Denali. Mm-hmm. Many of you probably know that. Mm-hmm. That plate is, that thick crust goes all the way underneath here. So this is an area of what we call flat slab subduction. So if you look at this schematic here, here is the area of flat slab subduction. This represents the highest topography in North America. But there's some interesting things along the margins of it. This shows that magmatic gap here. This was part of Emily Finsel's thesis at Purdue. We see a series of sedimentary basins, the Cook Inlet, the Tanana Basin where Fairbanks gets all its coal from, and we're located over here. So it's one of the few areas in the world where you have flat slab subduction, but one margin is dominated by big faults like the Denali Fault, the Tashenda Fault, the Duke River Fault. So years ago, Jeff Trop and I thought that maybe these volcanoes are related to just the strike-slip mechanisms themselves. But now we know that the geochemistry isn't consistent with that. Some of the volcanoes have compositions of what's called attacite. And so Bill Hart and his students think that as this flat slab comes in, it's melting along the edge. And that composition is very typical of young slabs and melting. But it's even more beautiful than that, in that some of these volcanoes are calc-alkaline. So there's some subduction-related component to them as well. One thing that's always been intriguing to us is that you have large glaciers that are coming off the St. Elias Mountains and pouring sediment onto this plate. And as that plate goes under, it's taking that sediment with it. These are the highest sediment accumulation rates in the world. And all that water and sediment, it's leading to these really large volcanoes. Some of these are 16,000 feet.
I mean, look at that thing.
You know?
I mean, this is an incredible stratovolcano
know.
that has no active oceanic plate diving beneath it. There's no trench nearby that's tied to this thing. And there's dozens of these that are along the margin of this slab.
And like I said, some of them are 16,000 feet. This one is at 12,000 feet.
I just find that wild and also embarrassing. I'd never really given it much thought till breakfast this morning.
But
So yeah, go ahead.
certainly perplexed us for decades.
Oh, yeah.
Now we think at least we partially understand it. We're a long ways from having it nailed,
Yeah.
obviously. But at least it makes sense in terms of this flat slab story. And it's consistent with the magmatic gap that we've been talking about.
Bald eagle, sorry.
Oh, yeah.
So just to finish this up, and we can toss in anything else you like. So if I'm super wide, the flat slab is beneath you guys, heading
Exactly.
north to the Alaska range. No volcanoes there.
No, well, because it's too shallow.
Too
Nick.
shallow.
Yep.
And, and go ahead.
What's important there, since you bring up Denali,
Yeah.
is that we always had this problem, like, why is the highest topography 600 kilometers inboard from the trench
Yeah.
and vary in a narrow arcuate band, and then it drops off on both sides? And we think it's related to the coupling. When you bring in this shallow slab and its interface with the upper plate, you get a lot of deformation, and that's why you have these sedimentary basins around the margin, the highest topography in the middle,
Yeah.
and volcanoes along the strike slip side.
So last thing maybe.
Uh-huh.
These guys are doing a nice job of fighting the mosquitoes to stand
They're
there.
very talented.
So well-known active Aleutian volcanic arc, subducting ocean plate. Before this thing shows up, and we just take all this all the way back to the south, which means we're also going back in time, is your number 30 million years ago when this raft starts to show up on the map. And before 30 million years ago, was there, do we presume, a continuation of the ring of fire going all the way around with a subducting ocean plate?
Absolutely. That's what Emily was able to show in her thesis. She looked at all the available geochronology over this area now where there are no volcanoes, and she took all the igneous rocks, so volcanic rocks and plutonic rocks. We didn't use any of the volcanic ashes because they could come from a long distance.
Yeah.
And she was able to show that through here you have igneous rocks, but they all turn off at 30 million.
Turn off.
And that's when these basins along the margins turn on. And 30 million is the magic number over here for the age of these volcanoes. So 30 million is like the lottery number. That's when everything.
But we start the arc 30 here, or are there older than 30 million year old plutons that talk about the old days before the Yakutat showed up?
They're all covered. We can't get to them.
Can't get to them.
What we do know is that they're older down here, and you can see where the active ones are. So this is kind of prograding northward, like a train tugging northward, bringing in sediment, melting the crust.
Oh, this thing's on the move along with the Yakutat itself?
They're a pair. They're a couple. And so
that's even more wild.
And this big thrust belt here is propagating in that direction, and here's the basin itself. So this is very much what we think the layer might look like, Nick. And so, you know, when we think about analogs for why do we have big block uplifts at the Front Range in Colorado and in the Wind River Range, it's the same kind of phenomena. And so this is really one of the best examples. And we think in the Laramide you had a flat slab as well with an oceanic plateau. And that's one of the things that Emily and I walked away from with her work, is that it made us really rethink the importance of high topography and flat slabs. So if you go to South America, you have this Altoplano plateau. It's related to flat slab. India is the ultimate example of flat slab. And so you have a big, thick piece of continental crust trying to go under Eurasia, and you form something called the Tibetan Plateau. Well, here's the example that I call the Talkeetna Plateau. Not too many people would go along with that term maybe, but you can see all of this high topography out here, the highest mountains in North America, and a lack of volcanism.
Beautiful.
So a lot of it works. We still have holes in it, but there's a lot of it that makes sense.
Last thing, where are we driving today? Are we just going to continue right up this margin of the flat slab and eventually get to the Denali?
That's where we're headed, and we're going to look at the rocks that underlie all of this are part of the Wrangell terrain, and
Okay.
it's a classic topography that Mike and Brandon have been working on, and other people since Davy Jones years ago. So we're going to look at what is the basement underneath of the Talkeetna Mountains and how does it relate to things like Brandon's been working at and Kodiak Island. But this is a real key component for Cordilleran tectonics. This is where the classic terrain concept of Coney and Davy Jones came into play. So we're going to look at the roots of that. We're going to look at the Denali Fault, a very active fault. And then we're going to go into North America and everything will be wonderful again.
Good job, Con. I'm just going to finish with a close-up shot over here. Thank you, map people.
Thanks, guys.
Is there more than one cone here?
There's a couple. There's one to the left that's covered in snow.
Man. You think a couple of these are taller than Rainier? Like Rainier's 14,400.
These are taller.
These are taller.
Some of these.
And wider.
Not that one. That one's 12,000. But yeah, some of these are the widest, you know, by volume. The largest stratovolcanoes on Earth. I think Stanford is like that, and it's at 16,000. And like I said, 3 of the largest volcanoes in North America are right there.
Not made by subduction.
Not made by subduction, or not apparently made by subduction.
So I don't know, Mike. Does this intrigue you at all? If there's a major tectonic question mark for volcanoes this big, geochemically, is there something that could be done to say, okay, this is not an active ocean plate subducting, but there's some other model that, or 2 different models that Ken and another group has that somebody could do something with the geochemistry or something else? Seems like a pretty big question with big mountains.
Yeah, it is a pretty big question with big mountains. I think geochemically it might be hard. So all this crust was affected by subduction prior to these being built. All right. And so if you're generating some of these magmas by melting the lower crust, you're melting subduction zone derived lower crust. And so you're going to end up with stuff that looks like it could be in a subduction zone.
You're inheriting.
Inheriting, yeah. And so if they're arising from just having a lot of mafic basalts basically interact with the crust, it's going to be hard. And I don't know, I mean, to be candid, I don't know much about the composition of these at all.
Right.
But I think you would look for things like Ken was talking about, like adacites. So those are intermediate magmas that have a strong garnet signature. All right. And so that can arise several different ways. But one way is like melting the downgoing slab. And so if we're really at the edge of the slab and there are adacites erupting over there, then that might tell us that, yeah, we're at the edge of a slab where we have hot asthenospheric mantle interacting with the slab, melting it. You're also probably producing basalt from the asthenospheric mantle coming up into the crust and melting portions of that.
Almost like those slab failure magmas, like in Washington. We had the 2 end members were arc magmas and then these slab failure magmas, and the adacites were the hot mantle getting shallower than it should be.
Right. Yeah. So slab edge and slab failure are going to be very similar.
Huh.
Yeah. In both cases, if you're at the slab edge, you have mantle that's coming up and around the edge.
Right.
And during failure, you break and you have a stenospheric mantle shooting up through the gap where you've broken the downgoing slab. So it's a very similar phenomenon.
But migrating with this thing heading north, that seems new. Like when you first mentioned this, that it was just outlining the edge of the shallow slab, I just imagined it was a line of everybody's the same age. But as this thing shoves, so there'll be newer cones showing up further north?
That's what a predictive model would say.
God. I find this wild.
I'd say
Yeah.
not quite on tectonics, but just for interesting things.
We're freelancing now.
We're speaking freely.
We're speaking. Do I have permission to speak freely? Yes, you do.
So one thing that I think about a lot these days with no real answer is just the lifespan of these volcanoes. They're very short-lived, arc volcanoes or these as well. So again, I don't really know the geology here, but like when you look at something like that, like Mount Drum over there, that whole mountain, that whole volcano is being emplaced in less than 1 million years. I believe just from like looking online a few minutes ago that we're talking about 500,000-600,000 years to make that whole thing.
Uh-huh.
And so that is extremely rapid and focused magmatism to have all that material come out in one place over that short period of time. And I just find that fascinating.
Why? Like that's true in the Cascades too. A stationary arc with 40 million years of magma generation, each individual point, you're building things just on the scale you're just talking about.
Right. So Cascadia is a great example. I'm much more familiar with that. So you build Mount Rainier, it's like not even quite 1 million years old. It's huge. You can see it from Seattle, right? You can see it from everywhere. And that just represents a very small fraction of the lifespan of the arc. Okay?
Right.
And so one of the things that I think must be happening is that you're having positive and negative feedbacks with how you get magma from the mantle to the surface. So some positive feedback to get it focused in one location. And then once it's focused in one location, there must be a negative feedback to ultimately shut it off on timescales of like 1 million, 2 million years.
Right.
And presumably that is stuff that's happening in the crust. And I don't know if we know what that is.
Huh.
But when I look at that, I'm always struck by like, that is a lot of volume that came out of the interior of the earth in a very short period of time.
Thank you.